In general, esters have very particular odors, and they are responsible for many artificial and natural flavors and smells. In this video, I'll be making pentyl acetate, also known as amyl acetate, which has a distinct candy-like banana smell. The reaction carried out in this video is a basic acetylation of an alcohol. Depending on the alcohol chosen to acetylate, the acetylation reaction can lead to very different and distinct smells, such as orange, banana, or even mushroom. For this experiment, I'm going to use 29 milliliters of acetic anhydride, 5 milliliters of concentrated sulfuric acid, 26 milliliters of 1-pentanol, 200 milliliters of saturated sodium bicarbonate solution, and 25 milliliters of saturated sodium chloride solution. You can also use 0.24 moles of an alcohol of your choice. In the bottom right corner is a list of the alcohols and the smell of their corresponding acetate derivatives. First, add 29 milliliters of acetic anhydride to an iced round bottom flask. Next, add 5 milliliters of concentrated sulfuric acid slowly and dropwise. The addition of the sulfuric acid is extremely exothermic, so it is very important to add it slowly and to keep the solution as cold as possible. It is highly recommended to have very strong stirring at this step. In this reaction, sulfuric acid acts as a catalyst. 26 milliliters of 1-pentanol was added to an addition funnel. I am using a pressure equalized addition funnel because it is much easier, but you can easily use something like a separatory funnel or a passer pipette. With strong stirring, add the 1-pentanol dropwise. This reaction is extremely exothermic, and adding too much 1-pentanol can cause the reaction to run away and effectively ruin our reaction. If you make sure that the reaction is strongly stirred, that the 1-pentanol is added slowly, and that the ice bath is constantly replenished, then this reaction should run well. Adding it slowly does take a while, so be patient. The reaction occurring is shown above. In general, this is how alcohols react with acetic anhydride. The oxygen of the 1-pentanol is going to act as the nucleophile and attack one of the carbonyls of the acetic anhydride. Both of the carbonyls of the acetic anhydride are equally likely to be attacked, but because the molecule is symmetric, the end result will be the same regardless of which one is attacked. For simplicity's sake, I've labeled one part of the molecule of the acetic anhydride as blue and the other part as green. I'm going to keep my explanation of the mechanism as simple and basic as possible. So in the first step, the oxygen of the 1-pentanol will attack the blue carbonyl. Then, the hydrogen, which is attached to the oxygen in 1-pentanol, will be indirectly transferred to the green oxygen that is in the middle of the acetic anhydride molecule. Then, as the final step, the bond between the blue carbonyl and the green oxygen is broken, forming the final products, pentyl acetate and acetic acid. I tried to keep my explanation as simple as possible, but if you want more information, a full detailed mechanism is fairly easy to find online using Google. After the addition is complete, remove the addition funnel, fix a thermometer, and replace the ice bath with warm water. Now turn on the hot plate and heat the water up to about 70 degrees Celsius. During this period, I placed the septum on top of the round bottom flask to prevent some of the water vapors from entering the flask and reacting with the acetic anhydride. Once the temperature of the water bath reaches about 70 degrees Celsius, you can turn off the hot plate and let the round bottom flask sit in the hot bath for about 5 minutes. 15 milliliters of cold water was added to neutralize any remaining acetic anhydride. As shown above, water reacts with acetic anhydride to form 2 molecules of acetic acid. The solution was then transferred to a separatory funnel. The round bottom flask was washed with about 15 milliliters of water, which was added to the separatory funnel. The separatory funnel is then capped and shaken vigorously with frequent venting. The layers are allowed to separate, and the bottom aqueous layer is discarded and the upper pentyl acetate layer is retained. This step washes away a lot of the acetic acid and sulfuric acid. 100 milliliters of saturated sodium bicarbonate solution was added. The reaction of the remaining acids with the sodium bicarbonate is quite vigorous. So before proceeding ahead to capping and shaking the separatory funnel, be sure to allow the reaction to calm down a little. Once the reaction becomes less vigorous, the separatory funnel is again capped and shaken vigorously with frequent venting. The layers are allowed to separate, and again the bottom aqueous layer is drained and removed. Be aware that at this point the aqueous layer and the organic layer might be a little bit cloudy, but that's fine. Again, the pentyl acetate is washed with 100 milliliters of saturated sodium bicarbonate solution, shaken, and the aqueous layer is discarded. Finally, the pentyl acetate is washed with 25 milliliters of saturated sodium chloride solution. After a thorough mixing, the layers separate and the sodium chloride solution is discarded. The saturated sodium chloride is used to dry the organic layer. The pentyl acetate was then drained into a 100 milliliter round bottom flask. A distillation apparatus is then set up. Pentyl acetate boils at 149 C, so everything that came over below this temperature was collected in the beaker and discarded. There might be a little bit of water that comes over with the product. If you are worried about any water in your product, you should dry it before the distillation with something like magnesium sulfate. The final product was then poured from the collecting flask into a dram vial. The final product has a very strong candy banana odor, but remember it was made in the lab, so you should definitely not eat it or even try it.